From the exam on Tuesday. I'll have them back for you hopefully this Tuesday, unless something terrible happens. If I get them done tomorrow or over the weekend, I'll post on Blackboard as soon as they're done, so you can check it out. I also have to finish grading those quizzes, so I'll do that too. We don't have much more to do, so pretty much just today, maybe a little bit next week, but I think we'll be able to finish it up today. And then next week we'll spend some time reviewing and getting ready for the final, which will be again on Tuesday, I always forget the date, sorry, 12th? Yep, 12th. Tuesday, December 12th at 1:45. This room. Close down on Blackboard to make sure. 1:45 to 3:30, so it's just a little bit shorter period. We have to stay within that grid so we don't conflict with other final exams. But it'll be a shorter exam, compensate for that. All right, so the last things we want to talk about, the last bits of chapter 11 are talking about reactions of alkenes, alkynes, and aromatic compounds. And then the last thing is we're going to look a little bit at functional groups. So before the exam, we talked about alkenes. We talked about their structure. We talked about naming them, cis trans, all that kind of stuff. What we didn't talk about was what they can do and why it's important. Like, what does it mean for a structure to have a double bond in terms of interactions with other molecules? Those alkanes that we learned first, they're kind of nice for learning the basics of naming and that kind of thing, but they don't really do anything. They burn, but they don't react with other compounds to form new things. And a nice thing about alkenes is they're more reactive, and so they can form new types of compounds, and we can use them to build new structures. So that's one thing we're going to look at today, is those reactions that they can do. These types of reactions are called addition reactions. They're kind of like combination or composition reactions, so two things adding together. And they can all be described as some sort of reagent, some sort of thing, adding to the alkyne, or to the alkene. So you have your alkene structure, and then something adds to it. So, as an example, here's what one might look like. You have your alkene. We'll draw the whole thing out so we can really see what's going on here. So you've got your double bond. And you can add to that some reagent like hydrogen, H2. Now, as it happens, this doesn't just happen by itself. So it needs a catalyst to help it along. And the catalyst that usually is used is some sort of a metal. So platinum, palladium, or nickel are some catalysts that you'll see. And you'll see as examples in the book that you only ever use one of them, but depending on what you're using or what you're doing, you pick whatever catalyst is going to work. So here's your alkene. We're going to call this, the thing that's adding to it, the reagent. And then this is the catalyst. And what happens in this reaction is those hydrogens from the H2 add to the double bond. So everything else here stays the same, except now there's two more hydrogens on that compound because those two hydrogens from the H2 have added to the alkene. So in this reagent, we go from an alkene to an alkane. Double under single bond, yeah. What? Right. Yeah, the hydrogen couldn't add there just and leave the double bond intact because otherwise then there'd be too many bonds to carbon. So in doing so, the electrons that form the bonds to carbon kind of go out and bond to the hydrogens instead. So you're ending up with a different type of compound. All right. So that's how we would write that out, like writing it out fully, all the different things there. But remember, when we just depict these structures, especially larger ones, it's usually inconvenient, or it's often inconvenient to write these kinds of reactions like this. So another way you might see it written is more like a line structure, like this. So if we started from that and we did the same thing, we add H2 with, let's say, a nickel catalyst. The product would be the same idea. So the two hydrogens would add to either side of the double bond. Oh, goggles on. And you'd have now an alkane. So what this looks like is that this reaction makes the double bond disappear. And it kind of does. But the way it does that is by adding more hydrogen. So if we look at this structure, remember that the line structure or the skeletal structure tells us there's got to be one hydrogen at either position there. And now in this structure, we need two hydrogens at either position because there's no more double bond. So there you can see the addition of those two hydrogens. This molecule is C6H10, and this is C6H12. So we've gone from 10 hydrogens to 12 hydrogens. Added those hydrogens on. All right, so that's how an addition reaction works. And we're going to look at one other type of addition reaction that gets a little bit trickier because it doesn't add the same thing to each side. So this type of reaction is called hydrogenation, adding hydrogen. And the other type of addition reaction we're going to look at is called hydration, which, what do you think we're adding in that reaction? Water, right? Right, when you hydrate something, you add water to it. When you hydrogenate something, you add hydrogen to it. That can be a little bit confusing. All right, let's do the same thing, but with water, and you'll see it kind of works the same way. So we've got our alkene. And we're going to add water. And I'm going to draw water in kind of an unusual way here. HOH, like that. The reason I'm doing that is because I want you to think about how similar this is to the previous reaction that was HH. So it's going to work the same way as the previous reaction. And now we also need a catalyst, but instead of a metal catalyst now, we use an acid catalyst. So sometimes that's written as H+, sometimes it's written as hydronium, some kind of acid catalyst. You need some acid to get this thing going. And then just like with the previous reaction, the H and OH add to the double bond. So the H adds to one side, the OH adds to the other side. The other H's are still there. The double bond is not. And we get an H on one side and an OH on the other side. The type of compound that we make from this is called an alcohol. This was an alkene again that we started with. And this type of a compound is called an alcohol. Anything with an OH group is called an alcohol. Well, with a couple exceptions that we'll talk about later. So we're turning an alkene into an alcohol by adding this water to it. All right, now if we were to do this in a line structure like we did the last one, same thing. If we take cyclohexene and we add water with an acid catalyst, then we're going to have OH on one side and H on the other side of the double bond. It doesn't matter which is on which side because it's symmetrical. But in a line structure or skeletal structure, we don't draw the H. We only draw non-H stuff. So that means that the product of this is going to look like we're just sticking an OH onto there. But there's also a hydrogen on the other carbon. Not just the OH, we're adding the H and the OH. Adding both things there. All right. So that's great, but what happens if it's not symmetric like this? What happens if there's actually a difference between the two positions? So let's take a look at that. Let's say we have this alkane, propene. If we try to do an addition reaction here, a hydration reaction, and add water to propene, two choices for how we could split that up. Because remember, H has to go on one side of the double bond, and OH has to go on the other side of the double bond. So let's draw both of those possibilities. So we get rid of the double bond, and we're going to add H to one side and OH to the other. And then there's another possibility, which is to add the OH to this side and the H to the other side. See the difference in those two? Those are not the same. Those are different molecules. If we were to draw them in a line structure, this one would look like this with the OH on the end. And this one would look like this, the OH coming off the middle. So those are not the same. Those are isomers. And so in this reaction, how do we know which one's which? Well, one isomer is actually favored. And the isomer that's favored is this one. There's a couple ways that we can say that. Whichever way makes sense to you is the way you should go with. One way is we can say that the OH always goes to the carbon that has the most other carbons connected to it. So you can see this carbon over here just has the one connected to it, whereas this one in the middle has two. So the OH goes to the one that's called more substituted. We talked about the word substituents, meaning things other than hydrogen that are connected. So that's going on the more substituted carbon. The OH is going to the more substituted one. The other way you can say that is the hydrogen goes onto the carbon with the most other hydrogens. So if you look at this structure, the H goes to the one with the CH2, the OH goes to the CH. On this one, the H goes to the CH and the OH goes to the CH2. That doesn't work. So whichever way you can keep that in your head, that's going to be the favored product, that's what you want to do. Let's try that. All right, so you can draw the product for that reaction. How would that water add to that structure? All right, we got a structure? When you do this, it's always, well, it's not always. You can either draw the two structures, the two possibilities, and then decide which one seems right based on those rules. Or you can just look at the two sides of the double bond and stick the OH where it seems to fit. In this case, the best structure is this one. So the OH is going to the more substituted carbon, the carbon that has the more other stuff attached, not this one. So you've got two choices where to put the OH, here or here. Two different carbons it could go at, because the OH goes on one side and the H goes on the other side. You want to put the OH on the one that has the most other stuff connected to it. And by other stuff, we mostly mean carbon, usually. All right. Let's try another one. For the product from that one. All right. You got something? So once again, you got two choices. You look at the double bond and you find, okay, which side does it make sense to put the OH on? So which side? Top, right? You got two carbons on the double bond, here and here. So you say which one has the most other carbons connected to it? It's this one. So that means that our product should be the one where the OH is there. The H is on the other side of that double bond. All right, so there's a whole bunch of other addition reactions. They're not in our book. If you go on and take more organic chemistry, you'll get to learn them and all their fun. There's some other things that happen with these types of reactions too that we didn't really go into. But that's just kind of a taste of it for now of what these things can do. Let's look at the next category of compounds, which are called alkynes. And those are the triple bonds. So that's compounds like this. Again, carbon has to always have 4 bonds. So if you have a triple bond between 2 carbon atoms, that means the only thing on the other side could be 1 bond, 1 hydrogen. The way you name alkynes is just like alkenes, but you use a Y instead of an E. So this molecule is called ethyne. But like with a lot of smaller molecules, it also has a common everyday name. So this is called acetylene. You ever hear that term acetylene, which is used as a flammable gas for things like welding, or like the gas that we formed in that pumpkin when we did that demo. This is the molecule that you're talking about. It's the smallest alkyne. Alkynes are linear in shape, meaning they're not bent. So this is an actual 180-degree bond angle, meaning it's totally just straight in a line. And because of that, there's no rotation around a triple bond, but there's also no cis or trans because they're perfectly straight. So there isn't like they can be, on the same side versus the other side. They're just all linear. So when we're drawing line or skeletal structures of triple bonds, we don't bend them. So let's say I wanted to draw this butane. Normally, in a single or double bond, we'd say, okay, we got 4 carbons, so we're going to do 1, 2, 3, 4 zigzags. But triple bonds are bent, and are not bent, they're straight. So we leave them that way in the line structure, and we just draw it like that. I don't know why that got all weirdly curled up. I'll try that again. So that's how we would draw that kind of a structure. Because of the starting and ending point of the triple bond, we can see the 4 different carbons, even though it's not bent. So there's our 4 carbons there. There's our 4 carbons there. So how do you think you would name that compound? Remember, there's no special rules for alkynes except that you use the Y instead of the E. But think of it as though it were an alkene. How would you name it? And then just put the Y in there. Close. 4 carbons. Yeah, butane. Butane. But remember, we have to be a little bit more specific here because there are different types of butynes. That's butane, but so is this one with 4 carbons. So what's the difference between those two? The what? Oh, wait, that's pent. I drew it wrong, sorry. Okay. That's another butane. But those have to have different names because they're isomers. So how would we make different names for those? Where the triple bond is, yeah. So how would we specify that in the name? Right, 1 or 2. So this one would be 2 butane, and this one would be 1 butane, just like with the double bonds. Same thing. You always say the number that the double or triple bond starts at to label where it starts. Alkynes can also undergo addition reactions. They're a little bit different, so we're not going to really go into that. Mostly just know that they exist, that they're called alkynes, that those are the types of structures that they make, that they're linear. And the next class of compounds that we'll look at are called aromatic compounds. Kind of. That's where the name came from, that these were compounds that had particular odors. And a lot of the kinds of like good smelling type molecules that we like, whether they're minty smells or like citrusy smells or floral smells, are in this category. But we've kind of specified or changed the definition a little bit to talk about a particular type of structure. So here's how that works. There's a molecule called benzene. Benzene looks like this. It's kind of like cyclohexane, but it has alternating double bonds around the ring. Because of that, it only has 1 hydrogen on each carbon. So its formula is C6H6. And just to be clear here, because this is a common mistake, this is not cyclohexane. Even though it has the same shape, cyclohexane has no double bonds and has 2 hydrogens on each carbon. All right, so benzene. Benzene is a pretty special compound. Because of these double bonds, it is extremely stable. So all those addition reactions that we just looked at, those don't really work with benzene because of its special stability. Its special stability is due to something called resonance, which is kind of a way of saying that there's 2 different ways you could write this that would be equivalent. So a little more room here if I can. So I can write it the way I just wrote it, or I can kind of shift all the double bonds over. And have pretty much the same structure. But if we think of those carbon atoms as individual atoms, those would be different. Double bonds are shorter than single bonds. So if they were actually two different compounds, we'd expect to see two different things in our sample. One where it had one set of short and long bonds, the other one had the other set of. And instead, what happens is it really represents an average of both of those structures. And so the real structure is an average of both. And so we kind of draw it in a strange way, where rather than drawing all those double bonds all the time, we just draw a circle in the middle. And that kind of shows that it's all even and that it's like an average of both. And it's unusual because we don't usually just draw a circle in a molecule, but that's what that means. So when you see chemical structures with benzene in them, or with this benzene type structure in them, they're sometimes still drawn with the double bonds, but they're also sometimes drawn with the circle instead. And that's all that means. It's an average of these two possibilities. Benzene, because it's so stable, is an extremely common structure in nature. It's a big part of a lot of biological molecules. So then that makes it a big part of things that are meant to interact with biological molecules, like drugs and things like that. So you'll see it all over the place in different types of compounds. It's also, because it's so stable, it is actually dangerous also. When it's by itself, like the benzene by itself, is a carcinogen. You know what carcinogen is? Right? What does that mean? No, everybody started out in there. It means it causes cancer. So a carcinogen causes cancer. Or can't, it doesn't necessarily cause, can cause. So for a long time, benzene was used as a popular solvent because it works really, it's a liquid, it works really well to do chemical reactions in, and a bunch of people got cancer from being exposed to this all the time. And now it's much, much less widely used. It's not really used in large quantities in industry anymore. We found other alternatives that work pretty well. There are solvents that are based on benzene that you can get pretty easily, like in hardware stores, things like toluene, that work well but don't have that same kind of carcinogenic effect because our body can process them a little bit more. There's another class of interesting benzene-like compounds called polycyclic aromatic hydrocarbons, or PAHs. And these are what you get when benzene hooks together in these different kinds of almost look like honeycomb type structures. So there's this one, which is called naphthalene. You can add another one on there and get anthracene. You can have like these kinds of things going on. This is called benzoalpha-pyrene. These are generally products of incomplete combustion. So if you combust something, if you burn it, and you burn it fully in plenty of oxygen, it should turn exclusively into carbon dioxide and water. We learned that a combustion reaction produces carbon dioxide and water. But in the real world, when something burns, it usually doesn't have enough oxygen to fully combust. And so it makes these kinds of products like this, and these are also carcinogens. And that's why anything that involves burning generally can cause cancer. So that could be like smoking for one. This is a big part of why smoking causes lung cancer, because the incomplete combustion of these plants in the cigarette ends up forming these types of molecules that you then get in your lungs. So the idea that like an additive-free cigarette or something, or like a natural cigarette, is better for you because it doesn't have added chemicals in it, it still will have these things because anything you burn is going to produce these things, which are then carcinogens. This is also true for things like cooking. Like if you eat smoked meats or smoked vegetables or smoked fish, that kind of stuff, these are some of the products that are getting in there from that incomplete combustion. Even something as simple as like grilling or cooking something over really high heat so that it gets that nice like charred kind of brownish blackish edge that's so delicious. That's not great for you. If you eat a lot of that, you're increasing your cancer risk. So these are the types of compounds that are produced by that incomplete combustion in those different scenarios. All right. The last thing we're going to talk about today, and really for the semester in terms of new information, is something called functional groups. We're going to do it a little bit differently than the book does it. The book, rather than talking about functional groups as a overall topic together, splits them up into these different pieces. So there's some in chapter 11, some in chapter 12, some in chapter 13, and kind of spaces them all out. We're not going through all the chapters in detail like that, so we're going to put them together in a little different way. But functional groups are the parts of molecules that control its reactivity. So the things on the molecule that actually make it do reactions, that make it do the things that it's going to do. And so really like the most important parts of the molecule. I had a meeting with some of the folks in some of the health careers programs last semester, and we were talking about like what are some of the most important things that people should know from this chemistry class before they go into like dental hygiene or nursing and things like that. And this was something that kept coming up because in those programs you have to learn a lot about these big libraries of molecules, whether they're drugs or materials that you're using, things like that. And they're always linked or grouped by functional group. So if you can spot and identify the functional groups, it really helps to be able to organize all of that kind of information. So for instance, classes of antibiotics, whether they're penicillins or tetracyclines or sulfonamides, those kinds of things are all grouped together by functional group. That's what makes them different, and they have different mechanisms because of that. So we're going to look at some of the basic organic functional groups, a couple of which we've already looked at, we've already known, and then we'll learn some new ones, and then we'll learn to identify them in the molecules. So let's make a little table. We'll have a group. We'll have the name. And then we'll have an example in a molecule. All right, so our first one is one our first couple are ones we've already talked about. What's the name of something like this? Alkene, right. So this is called an alkene, and that's a functional group because an alkene can do those types of particular reactions. So an example would be something like that. And there's our alkene functional group right there. Today we just learned about alkynes. Same thing. And we also today learned about aromatic functional groups, like benzene. So this can be like in a much larger type of a molecule, like with that circle. This is ibuprofen, the pain relief medicine, and it has an aromatic functional group right in the middle there. All right, those are the carbon-based functional groups, the ones just based on carbon. And now we'll look at some that have some other atoms in them as well. Remember what that OH group is called? We mentioned it today, but didn't really make a big deal about it. This is called an alcohol. Here's a flavor molecule called eugenol. It's the major component of cloves, but it's also in a lot of other kinds of flavoring. And it has an alcohol there. So when you look for that OH, that's called an alcohol. If you have an oxygen that's surrounded by two other carbons, like that, that's called an ether. This molecule above has one of those in there. There's another ether. Ether was, that particular molecule is also just sometimes known as ether, diethyl ether. It was used for a long time as an anesthetic. You can inhale it and it kind of knocks you out. It's really dangerous though. You can die from it pretty easily from an overdose. It also is really unpleasant, leads to a lot of vomiting and things like that. So they don't use it anymore. We still use it as a solvent. It does a lot of nice chemistry stuff, but we don't use it for that medical purpose anymore. And then there's several types of functional groups that are sometimes a little difficult to tell apart from each other, that all are based on this carbon double bond oxygen. It's called a carbonyl group. And we'll look at the different functional groups. If there's an H on one side of them, it's called an aldehyde. Like formaldehyde is an example of this. Aldehydes are important compounds in a lot of ways. They're very smelly, so you can sort of pick them out that way. If there's no hydrogen, but rather there's a carbon on both sides, that's called a ketone. A ketone is a product of sugar reactions generally. So carbohydrates. It has a pretty distinctive smell, kind of like acetone, like that nail polish remover smell. I'm skipping the examples right now because we're going to kind of do them all together when we get through this category. If it has an OH on one side It's called a carboxylic acid, or sometimes just an acid. So this is a way that organic acids have a functional group. So things like acetic acid, or what other ones did we look at? That one we looked at in lab, the amino benzoic acid, was it? Something like that. If there's an O on one side, but then more carbon stuff, that's called an ester. By the way, you're not going to have to memorize all these. Don't worry about that. What's going to happen is you'll have to pick them out of a structure, but you'll have a chart to help you. And then if you've got that same carbon double bond oxygen, but then a nitrogen, it's called an amide. All right, so that's a group. We'll put those all together, a group based on these carbon double bond oxygens that are all very similar looking. And so you have to focus on the thing that makes them different. The thing that makes them different is what's attached to one side of the carbon. Is it hydrogen? Is it carbon? Is it OH? Is it O with something else? Or is it N? That's the important difference there, the important thing that separates these from one another. All right, a couple more to add to the list. SH is called a thiol. And a nitrogen without the double bond oxygen is called an amine with an N. All right, so let's look at some examples of different molecules and see if we can pick out the functional groups. So grab your chart. I'm not going to leave the chart up on the screen, but you've hopefully got it written down. And we'll look at some molecules and try to figure out what's going on here. This molecule is called vanillin. It's the major flavor component of vanilla. What functional groups can you find in that molecule? What kinds of things in the molecule are going to control its reactivity, control what it does? Let me know when you see one. So look back on your chart. Try to find the pieces of that molecule that fit with those groups in that chart. You should find four different pieces that are on that chart. Anybody see one? Alcohol? Where? Top, right? Yep. So there's, I gotta use another color. There's an alcohol functional group. What else? What? Carboxylic acid, not quite. Similar. Yep, you got the aromatic, which is here. Aldehyde, that's it. So over here is an aldehyde. It's not a carboxylic acid because it has just H on one side of the C double bond O, not OH. If it were OH there, it would be a carboxylic acid and it would be a different molecule. It would do something different. Okay, one more. Can we find one more functional group there? Anyone? It's not quite an ester, but similar. No, I mean, that kind of goes in with the aromatic, but because it's all together, it's not. It's this one right here. That's an ether. It's an oxygen with a carbon on either side. Right? All right, let's do a little bit smaller one. This is the major component in garlic. So sulfur-containing molecules like this tend to have strong odors. This is that garlic smell. So I think we got two functional groups in here. What do you see?
Alkene.
Yep, alkene. And what else? Thiol, yeah. So we're pretty much looking at anything that isn't just carbon. Single bond carbon is considered a functional group. That's stuff that can do stuff. Okay, what about this one? This is carvone. This is spearmint oil. Oh, spearmint flavor. Oh. What kind of functional groups can you find here? Anybody see one? Ketone, yep. You got a ketone right here. What else? Not much else here. Double bonds, yeah, what are those called? Alkene. Is that it? Yeah, there's another one over here. That's it. To be careful about with this one, that ring in the middle is not an aromatic ring. In order for it to be aromatic, it needs to have that alternating double bonds all the way around. That leads to that kind of circle structure where all the electrons are shared. Because it doesn't have that, it's not aromatic. It's just a regular alkene. All right, another one. I'm not making this up, I swear. This is cocaine. Yeah, it's technically the what's called the freebase version of it, where it's been deprotonated. So, if you've ever smoked crack, this is kind of like crack. So let's find them in here. Should make this a little nicer line here. Ether, where do you see an ether? Down here? Yeah. Actually not an ether. It doesn't have to do with the weird thing. It has to do with the fact that it's next to this carbon double bond oxygen. So that makes it a different kind of a functional group. What is that? Yeah, that's an ester. So be careful with that. Because an ether, it looks like an ether because it's an oxygen in between two carbons, but one of those carbons has the double bond oxygen, which makes it an ester. What else do you see here? What? Aromatic. Aromatic, sure. Another, nope, not another ether. It's not a, excuse me, it's not a ketone. You're talking about this one over here? So remember, you have to think about what is it, when you see the carbon double bond oxygen, you have to think about what it's connected to. So in this case, what type of functional group would that be? Yeah, it would be another ester. Because directly next to it is an oxygen. So it's just like this one. Carbon double bond oxygen with an oxygen just directly connected to it that's connected to another carbon. So that makes it an ester. And then the last one, there's one more. Yeah, make sure it's going with an N, not the D. The D is the one that's next to a double bond, carbon double bond oxygen. All right. So you can do that? Yeah, if you got the chart, you'll be fine. Okay. We'll stop there then. So next week we'll have a quiz on, we said Tuesday, I think, right? Because we have more time on Tuesday, so it makes sense because we got the lab and everything. There's no lab on Tuesday. It's just lab checkout. We have to go in and get everything cleaned out and whatever. And so we'll have the quiz. We'll do checkout. Whatever time is remaining, we can start reviewing for the final. And then Thursday will also be final review time. All right.
So
have a good weekend, everybody.
Is what?
Quiz on Tuesday is everything.
Everything?
Everything.
Like from the beginning?
From the beginning.
What? And how much questions are they?
It'll just be a few questions. So it'll be kind of like some odds and ends, random stuff.
Promise just to keep polarity out of there.
Yeah, man.
No, I can't promise that. I'm sorry.
Oh, just one quiz without polarity?
It's an important thing. I mean, I don't know. I'll have it on there, but it'll be like a handful of questions from the semester, and I'll try to kind of space it out so there's no more than one question on any one topic. So that way you can have a sense of like, oh, I totally forgot about that. That's what I really need to work on, really study.
Cool.